Alright, so in the last class we studied the two elements, structural elements, which are most commonly. One is the bar, which is used obviously in all the structure, trusses and all the things, and also the linear spring. Right? This is not the torsion, but this is just linear compression and tension. Right? Now we want to draw the spring, the internal energy for a torsional spring. That means that if you have a torsional spring and you apply a little bit moment to it, then how much energy will be stored inside the spring, right? So what should I do? All right. The internal energy is the external work that I apply to compress it with angle phi. Start from angle 0 and I compress it to angle phi. So that is equal to integral m d theta from 0, no deflection to theta is equal to phi. Right? But what is the moment when you reach to the angle theta? Let's say you reach to the angle here, somewhere between theta, and theta is between phi and 0. So what is the relation between moment and angle theta? Moment is equal to k times theta. Exactly like linear spring. Linear spring is saying force is equal to k times deflection x, or delta x. Here we say moment, but the torsional analog to force is moment. So moment is equal to spring constant times theta. Right? Plug it here. So you get this is equal to integral instead of m, you write k theta, d theta from 0 to phi. Then you take the integral k theta squared over 2 from 0 to phi, and that's going to give you k phi squared over 2. Right? So this is the expression for internal energy. So Ui, internal energy, is equal to k phi squared over 2. So at the end, your moment is equal to k phi, right? So instead of phi, we can say phi is equal to m over k, and put it here. Then you get internal energy is equal to k over 2 phi squared, which is m over k squared, which is m squared, m squared over 2a squared. And that's going to give you m squared over 2k. So here, for a torsional spring that is subjected to a moment m, then you get internal energy y is equal to m squared over 2k. Now compare the linear spring with the torsional spring. What do you see? It's the same thing. All is converted is moment is converted to p and vice versa, which is exactly what we expect. Right? So now these are the very common structural elements we use or model. But nothing is perfect bar, nothing is perfect spring. Everything is a combination of these guys, right? Now what's the next very common structural element that you use? that we haven't included this yet. Huh?
Okay.
Yeah, cable. Cable can be modeled with just a tensional bar, a long tensional bar. Not compression, only tension, one-sided. So it's like unilateral component like that. What else that we have used so far a lot? What? Beam. Bar is right here. It's bar, right? A beam, right? So if I have a beam, let's say, now I want to make a plot that resembles a beam, hopefully. So now this is the beam. And you have moment of inertia, E, cross-sectional area, and then you have some couple moment distribution, M of X, and this is applied like this way. See that? So for this element, I want to find the internal energy. That means if I take this beam and fold it up like that, twist it, how much energy from my hand is stored in this beam? Because I know the moment I release it, it's gonna bounce back and move, right? Like exactly like a spring. So in order to find that, I say, well, if I consider this beam and cut it up into smaller parts, so you see this is my decomposed beam. So let's say this U beam, and you have a moment, non-moment here. At any point you have moment at X, at any point. So the moment is not constant, the moment can be variable. So what I would say, what would be the energy to bend, let's say this is d theta, so we cut it up into infinite number of infinitesimal slices. For each one, we have d theta deformation. So what would be the energy required to bend this amount of d theta? It's going to be the external work, which is half of the final moment here times d theta. You remember we had half of force times the final force, which was P times delta deformation. This was the external force that we applied to reach from force 0 to P. You see the linear plot I made for the force last time? We computed the area. We computed the area under the curve, and it became half of P times delta. Remember that? So that's exactly the same analog. So you get half of, instead of P, you got moment, instead of the linear deformation, you got angular deformation, d theta. That's exactly the same. So how do you find it? You just do exactly what we did, and last class you find is, but this is just rotational, M1. Right? So for each one of those, I have half of moment at that X times d theta. Here, half of moment at this X times d theta. So what should I do in order to find the energy of the entire group? Let's say you have two blocks, and each one has an internal energy U1 and U2, right? So what would be the total energy of the entire thing? Just a linear scalar summation, algebraic summation. That's the advantage of energy method, because it converts in vector complicated equations of Newton and equilibrium into just a simple scalar addition. The energy of the entire thing is the summation of energy of each thing. It comes from thermodynamics law. We already discussed in last class. So here, if I want to find the energy of the entire thing, what should I do? Just add these small, little infinitesimal energies. That means I should do summation of half of m at xi delta theta and I for any I, which I goes from 1 to infinity because I have infinite slides. So what do you think this summation should convert at the limit when I goes to infinite? So I have infinite number of slices. Integrate. So this becomes the integral of m d theta half of m d theta. From where to where? From 0, right, to the entire length of the beam. Length of the beam. So that's my internal energy. So this is the energy that is summation of all these little parts. Right? So this relation is a good relation. So in fact, we can summarize it like ui is equal to integral half of m of x d theta, and this is also a function of x from 0 to f. But I know that from my double integration method that d theta dx is what? M over ei. This relation, I had it in double integration method. That means the first integral of m over ei is the angle, theta. The second integral is v, for deflection. You see the first integral is the theta itself, right? So I had this. So instead of e theta, I replace this equation. So what I get, internal energy becomes integral from 0 to L. I already have a half here, mx. Right? I put this guy, now instead of d theta, what should I put from this relation? You see how I'm replacing this theta, d theta from this relation. So what should I put it? M of x over ei d x. That's it. This is d theta. This is y d theta. You see that? Now those things in the calculus you drive, it shows that it's useful because you always said, well, I solve for differential d theta, then get m over your dx. So what's that? What's the advantage of that? Well, the advantage is you can plug it here and get the internal energy all in the term of the moment distribution. Why we do in term of moment distribution? Because we already know how to find moment relation for the entire beam, right? Using Heaviside functions. So this becomes, if you simplify that, this becomes 0 to L m squared over 2ei dx. So that's the final relation. So I write it here. Internal energy of a beam is integral from 0 to the entire length of the beam. The moment relation squared divided by 2ei dx. So I have my table completed right now because I have all the useful structural elements that I encounter in this class, right? There are other elements. Can you mention just one of them that are not in this table? Well, that's right. Cable is not in this table. But as I said, the tension form of cable can be modeled with a bar, right? What else? Like, just look at your car. The body of your car. What is made of?
Frame.
You see, the frame can also be modeled with beams. Just the body. I mean, I'm talking about the surface.
Sheeting.
the plate, right? So we have another structural element, it's called plate. So plate is in fact a finite length and finite thickness. Finite thickness. Infinitesimal thickness. That it has its own relations. But look, can I apply energy method to the frame, to the plate? Yes. As long as, where can I apply the energy method? That is right, internal energy is stored in a plate, which is like a spring kind of analogy, is equal to my external work that I spend on it. Where can I write this? When you have the assumption of, you remember we had external heat, the heat transfer and noise and all the dissipation, nonlinear. When you actually apply your force very slowly, so your object is always in equilibrium, so you don't have a rapid heat transfer, you don't have nonlinear effect, you don't have breakdown, right, noise generation, you don't have, so this exactly is still valid for plate. But because in this course we only consider those elements, we all also consider the energy method of this element too. So now let's move on to Castigliano theorem, which is probably the most important thing in this class. And you always have a question in the final exam, maybe two, from Castigliano. So in the Castigliano theorem, my objective is to find, if I have the internal energy, somehow I should find deflection. Because what is important for me is the deflection. It's not the internal energy, it's the value of deflection. So let's say you have an arbitrary body, this big potato, again, this just could be anything inside it. The truss, the frame, anything, arbitrary. And let's say you have some loading on it. P1, P2, P3, arbitrary. So this theorem is very general, Pn, right? Arbitrary number of loads anywhere, right? So you can write the internal energy is equal to the external load that I apply to this object. So that means initially you don't have any of these guys. So this object is at rest. Then you add a little bit P1, right? In order to move, because this is sort of moving, then you have to constrain it, have some opposite direction in somewhere in order to keep it in equilibrium. Then you add a little bit P2, P3, Pn. Then the work that you spend to keep it in equilibrium is equal to the energy stored in this spring, right? So originally you have this. Now let's say we add a little bit force to this, only this point, right? P1. Let's say you add a little bit delta P, EP, from the cruise. So your object is already in some sort of equilibrium, and then at one particular point, for example here, point A, then you add a little bit extra force to that P1, right? So what happens here, my external work is going to be added by the amount of external force that I spend. And this is also going to deflect at this particular point, like that. You see? Some sort of exaggeration, like that. The rest is too much. You may get some deflection somewhere else, but we're talking about the deflection at this point. Let's call it delta. So delta is the deflection completely along this line of action, right? So it's not vertical, it's not in the X or Y, it's in the direction of P1, whatever it is, right? So the external work from the equilibrium is right here. This is the initial equilibrium. Let's say now, when I apply a little bit delta P to P1, then the external work, which is initially UE, is going to get added to P delta P1, the value of force times the deflection, right? Because that force, delta P, is just very infinitesimal, right? You remember if you had final P, right, over the delta, then the integral under this external work was half of P times delta, right? But in this case, because this P is just infinitesimal, then just delta P times delta is the external additional work that I needed to add this in order to transfer this system to a new equilibrium, that I have some delta deflection. Now, what would be the internal change? So the internal function, you see, originally is a function of UI, is a function of P1, P2, P3, Pn, right? Now when I apply a little bit extra force to P1, then how much this would change? Now we're talking about differential. You remember the differential, for example, F of P1, P2, Pn is like a function of several variables. The differential of F is partial F, partial P1, delta P1, plus partial F, partial P2, delta P2, plus dot dot dot, plus partial F, partial Pn, delta Pn. This is what we have in calculus. The differential of function of arbitrary number of variables is the derivative of function with respect to that variable times the delta in that variable. Now, I know that the only differential that I have is all the same. It's in one variable, P1, right? So I can just say, because I have no change in P2, 0. No change in Pn, right? So only change is this guy. So I can just eliminate the rest of it. So what should I write for the change in internal energy when I apply a little bit force to P1? It's going to be UI plus partial UI partial P1 delta P. Delta P1, which is delta P. The amount of extra force that you have P1, right? So what can I simplify this equation? What should I do to simplify this equation? Look at this. UI is equal to UE. So this guy will cancel out with this, right? Because they are equal, right? So what else you get? You get the derivative of internal energy with respect to that P, like this P1, right? P1 times delta P is equal to delta P times delta. Obviously, delta P cancel out. So what do we get? The deflection is equal to derivative of internal energy with respect to the force applied to that point. So you write the statement like that. The deflection at any point is equal to the derivative or the first derivative of the internal function with respect to load P1 applied to that particular point. This is very important. In fact, this is mathematical form, and this is the explanation. It says the deflection at any point, for example, this point, is equal to the derivative of internal function with respect to a force that applies to that particular point. Right? So if I want to find deflection at this point, what should I write? You see, if you apply a little bit PG here, it's going to deflect, right? Yeah. So what would be delta at this point B? Huh? Partial UI, partial P3. So if you take derivative with respect to any particular forces, you get deflection along the line of action of that force. Look, this deflection is not in X and Y, it's along with the line of action of that particular force. Right? Example. So because I don't want to erase this, let's put it here. Not in the table. Let's put it in the corner. The deflection is equal to the derivative of internal energy with respect to that particular point. Force applied to that particular point. So now I can erase the proof. This is kind of proof. You just do it once and you never want to repeat it. Just to understand how these things are derived. All right, so example. P, E, A, F. So you have a bar, and then you apply force P at the end. Everything is parametric, so it's going to be formed like that. Now, the question is, use Castigliano theorem to find deflection at point A. Let's say this point A, then this moves to point A prime, right? Like that. Then find delta A using Castigliano. First of all, before I do Castigliano, just don't use Castigliano theorem. How do you find the deflection at this point? Just back to mechanical material, chapter 1. So you write sigma is equal to E epsilon, Hooke's law. And what is sigma? This force. What is force? P over cross-section area, right? Is equal to E times the deflection over initial length. So your delta is P L over AE. That's what you get. So we know the answer. Now we want to use Castigliano theorem in order to find the deflection here. And what should I get at the end? PL over AE. Like if we get something else, we have the students in the exam say, well, because I use Castigliano, he's equal, for example, P force L, the square root of L over A. That's what we got, for example. And I said, well, this is very different from this. And so, well, because I use Castigliano. That's the reason. Well, whatever you use, you should get exactly the same result. It's just a different approach. So what should I do in order to use Castigliano? This Castigliano. So what do I need to find this deflection? Internal energy. Right? So you kind of, even if you don't have a force here, you kind of, the way you start with Castigliano, you add the force if there is nothing there. If there is a force, that just use it. If there is nothing there, you just add a force with P, parameter, not the value, like 2K, 2K. Just the actual parameter force P. And then the next step is find internal energy. The final step is take the derivative and find deflection. So the steps are, first, add a force P in the location you want to find the deflection if there is no force P there. To find internal energy in terms of that particular force P. So your internal energy also is not a number, it's a parametric function. 3 delta is equal to take derivative with respect to P. So let's do it. So what is the internal energy here if I have a force P here? Internal energy is equal to, I go to my table. In the test or exam, you have this in the appendix, in the last page. So you go to the table, what kind of element do I have? The bar. So the internal energy is P 2 L over 2 AE. So I already have step 1 done. Step 2. And also step 2 done. But I already have a P here. Already have my internal energy from the table. Right? And then the last step, what should I do? Delta at that point, A is equal to the derivative of internal energy with respect to P. So what do I get? The derivative of this with respect to P? So this is constant, L over 2AE, right? Just factor it, L over 2AE, factor it out. So you have get derivative of P squared with respect to P. And what is this? You get L over 2AE times 2P. 2 cancel out the P, so you get PL over AE. The same. Right? Now you may say, well, this just, I like this method. This is not useful. Now I'll give you another question. Find, and this is the second question. That's the first question. Let's just write it here. I don't want to erase anything. So let's say you have this configuration. So this is for A1, E1, L1, A2, E2, L2. And you apply the force 2K here. And I want to see now your point, let's say this point B. I want to see how much my deflection is at point B. Well, if I use this method, the original method that the stress is equal to E times epsilon, then this is not straightforward because your stress is different. Here you have a different stress because you have different cross-sectional area here. So you have to jump in the axial stress, right? So how can I find the deflection at point B? Internal energy is very straight now. Why? Because internal energy, let's just write it right here. The total internal energy is equal to U1, summation of internal energy of this guy plus internal energy of this guy. right? U1 plus U2. And what is U1? Come to the table, because every one of them is a bar. So you get P. Now let's say instead of 2K, this guy is actually a parameter, P. So one of the objectives is the first step. Even if you don't have the parametric force P, you have to kind of play with this force, make it a parameter P. Because you want to take the derivative. If you have a constant, the derivative becomes 0, right? So you make this P at the end when you evaluate it, instead of P, you put 2K, right? If there is nothing here, but then maybe you load maybe somewhere else, and you want to find deflection here. Then again, you add P, and at the end, you put P is equal to 0 if there is nothing there. But here we have actual 2K, right? So U1, what should I do for U1? P squared, the force inside element 1. What's the force inside element 1? If this is P, what's the force inside element 1? P. If you plug the normal back to mechanics of material, chapter 2 or 3, if you draw the normal force versus X, then you carry it like positive P, tension. Everywhere is tension, positive P. If you draw the actual load, right? So you put P, instead of here U1, you put, let's use integration. So P squared, right, times L1 over 2A1 E1. Thoughts? U2. What should I write for U2? Not the same thing.
Something like L2.
The same formula. Yeah, the same formula, but you just use again P because the actual load is P. P squared. Then you have L2, 2A2, E2. That's it. Right? So what would be my deflection then? The derivative of Ui total with respect to P is my deflection at the point that P is applied, which is delta B. That is equal to, take the derivative. So you get 2 P L1, 2A1, E1 plus 2P L2, 2A2, E2, and that's going to give you P1, L1, A1, E1 plus, which is P, L2, A2, E2. Right? This P cancel out. So you get PL1, A1, E1, PL2, A2, E2. Right? Which you can write it as P times L1, A1, E1 plus L2, A2, E2. So that's your formula for deflection. Interesting. So what does it mean? Look at that formula. What does it mean? Compare it with the first formula. What does it mean?
That would be your K value.
Yeah, the inverse of that is your K, right? Because if you write P is some K on delta, 1 over this, it goes to the other side, become K. What's the other interpretation? Compare this with this one, when we only had one bar.
Add in series.
Yeah, that means that your total deflection, expand this, you see, is just the summation of the deflection of each bar independently. You see that? And this comes from the integral, the derivative. It doesn't come from intuition. Good thing about energy method is extremely machinery procedure. You don't need to have some sort of intuition about sun or 3-dimension or all you do is just find the internal energy and you take derivative. You don't need to have any kind of physics intuition. It automatically works. You see, we didn't say that a deflection at this point is summation of deflection of each individual bar together. That's kind of physics intuition, right? We said just close your eyes, find the internal energy of the entire thing, assembly, take the derivative, and then you get the deflection. But this gives you the intuitive result. Another thing is, if I want to solve this without using the energy method, Castigliano, what's the next easiest method that I can use? We already discussed it before. Find the K for each one, or method of combining springs. That we've already discussed. So that means that if you replace this guy with a spring, and this guy with a spring, what's the spring constant for this? K1. We need a new column for a spring constant. So AE over L was the spring constant of the spring, right? So here you get, if you don't believe it, you can do it, right? P over A is equal to E delta over L. Then write this as function of P is equal to AE over L times delta. So that's your spring constant, right? So here a spring for constant for element 1 is A1, E1 over L1, K2 is equal to A2, E2 over L2. So 1 over K total is equal to 1 over K1, 1 over A1, E1, A1, plus 1 over K2, A2, E2, L2. Now if you do that, you can see that the L1 comes to the top, L2 comes to the top. And if you invert the entire thing, you get the spring, the inverse of that. So they are exactly the same. So it's just your call. What method you love? Right? Yeah.
In real life application, is there a time where one or the other method is better to use?
Always, in the real life application, always the one that is based on intuition and a slight simplification. So I would say 99.99% of the structure we have in real life is indeterminate, heavily indeterminate. So the way you do it, you convert everything to pins, right? And then, what does it mean? That means that you use your intuition. You just don't close your eyes, write the energy function for the entire structure, take derivative. You don't do that. You just simplify. And then you say, well, deflection of here, maybe the spring method is your next guess. I combine this element to like 3, 4 spring, and then I simplify the deflection.
So if we do, in this scenario you're talking about, if we do both methods, we'll get different answers. In a real life indeterminate.
In the real life indeterminate structure, because if you use, for example, the spring method, you actually do a lot of simplification. You don't do the internal energy of indeterminate structure, right? And then you get the answer, and then when you use computer, the computer does internal energy. So computer is done. It goes to find every single element in your structure. How does it find it? It goes to the CAD file we create. It loops over all elements. How does it know that this is being this bar? Well, you draw it. We define it for computer. Right? So even computer is dumb, it knows what kind of category it is. It put it all together, and then we have something called numerical differentiation. If you take numerical analysis, then you realize how computer can take different, derivatives. Then the computer just takes derivatives in like fraction of second for a structure with 2 million bars. So what approach computer use? Energy method. And
You have to define it first using.
Yeah, but the way you do it, you say, well, this big, huge thing, I can see it because I'm human, right? I don't see the numbers, I see the meaning. And then I can simplify it into 3 springs. Well, the one that you do is good, intuitive, fast, but it's not accurate. The one that computer does is extremely expensive, but because computer is dumb, it does it anyway. But that's more accurate. All right, so let's have let's say if you can solve this problem. Let's make this actually as a quiz. But what I do, I make it, if you solve energy method, this method using energy method, you get extra bonus.
How is this
More papers. Did you get extra paper? I didn't bring enough papers today. You may just go ahead, please, and use extra paper from your own paper. Yeah. If you still need a paper, I'll try to figure out what I need to do. I think everyone has an extra piece of paper that we can use. So this is a simple problem. Just put here this extremely simple problem. So you have the beam and this force applied to here is equal to, let's say make it P, and from here to here L, from here to here L. Let's say values are, we can solve it parametrically, or we can use 2K here, 1 meter, EI is equal to also 1. And this is what? Find deflection at point C. A, B, C. So what happens here? You get delta C, vertical deflection. Use double integration. To find delta C. And then let's make this another meter waiver, not extra bonus, Castigliano. Castigliano's theorem. To find delta C. You should get exactly the same result. So the second one is optional. As you can see, this is optional. But if you can solve this, you get meter waiver. And everything you need is in this table. Fact, Let's make this as final here. Make that final here. For Castigliano, for double integration, you may get a few lines, right? Even if you use heavy start, the ceiling you do first integral, second integral, apply boundary condition, right? For Castigliano, you just get one line. No boundary condition, no double integration. You want to say deflection is equal at point C, derivative of internal energy with respect to E at C. So this is important part. Derivative of internal energy with respect to P that is applied at point C. Right? So it's applied at point C like this. Not this P. Let's just say this 2K. See that? Not that P. The P that is applied at point C downward. drawn with this figure, the picture, not the formula. The formula is done. Can you find the problem here?
Yeah, the M should be pointing the other way.
You see, if the M is this way, with the right hand, then the direction of this twisted curve should be the other way. This way. Like that. Minutes. The double integration shouldn't take that long. It's pretty easy. Assuming that you have done the homework, the last homework, it should be a piece of cake. Very easy. Now you see the Castigliano is even easier. Do another 60 seconds. Also, ready? Don't forget to write down your name, please. All right.
I got a super bad version. Okay, so
You got like, I had like, yeah, I got 3 out of like 6 sets. The integration was
So double integration method, you know that the second derivative dx times dy is moment at x. So what you need is the moment relation, right? So if I make a PDF of this, then you have a 2k here, 2k, and then you cut it somewhere on the left, mx, and you have v incredible it, over mx plus 2k, every side x minus 1, plus 2k kilonewton meter, 0 minus 2k times x, 0. Right? And then mx, solve for mx, and you get, take 2k to the right, then you get x minus every side, x minus 1, minus 1. So you get this relation. So what you do, here, you have EI, which is basically 1. Look at here, EI is equal to 1. You can keep EI because it's constant, but I just simplify. So second derivative of v with respect to x is equal to moment relation, which is 2k times x minus every side x minus 1 minus 1. That's what you have. So what do? You integrate it first time, so you get dv dx is equal to 2k x2 over 2 minus x minus 1, 2 over 2 minus x plus c1. One more time, vx is equal to 2k x3 over 6 minus x minus 1, 3 over 6 minus x2 over 2 plus c1x plus c2. And then you apply boundary conditions. What are the boundary conditions? Deflection at x0 is what? 0. Deflection at x is equal to 1 is equal to 0. So you get c1, c2, and then you evaluate v at x is equal to 2. This point here, point C. Yeah.
The deflection at 1 shouldn't be 0, should it? It should
At,
be that angle was 0.
Yeah. Sorry, I thought there was a roller here. That's right. Then you do deflection at 1, 0, derivative of deflection, and x 0 is equal to 0. There. So both the slope at 0, 0, the deflection at 0, 0, right? I thought I gave the roller problem here. I wish I could. So my intention was to give you a roller problem because this is just very simple. It's extremely simple. You don't need to even come to take 2 integral and apply one equation. You can immediately get rid of C1. Why? Because the slope is 0. And then C2 become very easy. So this is extremely easy problem. Now, what about the energy to Castigliano? What about Castigliano? Castigliano says the deflection at point C is equal to the derivative of internal energy with respect to P that applied at that particular point in the direction you want to find the deflection. Now, if you want to find deflection in the X, we apply a P right here. If you want to find deflection in the Y, we apply P in a Y. Look, I don't have a P, so what should I do? Quit. Add a P. And then finally, when you evaluate it, what do you put for P? 0, but there is nothing here. Right? I just add it. just for the purpose of taking the derivative, because if you don't put there, the derivative becomes 0, right? So if I add a p here, what do I get? Zero FPD, then you get p here. You already have 2k MA AY, right? So you solve for MA, you get MA negative 2k times 1, negative p times 2 is equal to 0. So MA is equal to 2, factor out the k2, so you get 2 plus p 2 times p plus 1, right? So this is your MA. And AY minus 2 minus p is equal to 0. So you get AY is equal to 2 plus p. So here, put 2 plus p, and MA, put 2 times p plus 1. Now, this is your FPD for arbitrary p. Don't forget, we don't fix p to a value. Why? Because we want to take derivative. It should be like a parameter. So my p, arbitrary p, will show up at the support reaction. Now let's say if p is equal to 0, what is the reaction? You see? And my actual physical problem is when p is equal to 0. But I don't impose it right now. I impose it at the very end when I finish all the calculations. So now, moment relation. I know that Castigliano wants the internal energy. What's the internal energy? Right here, right? So this says the derivative with respect to p of the internal energy of beam. What's the internal energy of beam? Integral from 0 to length. From here, let's say this is 0 to the entire length to, right? The moment relation, the square over 2 EI is equal to 1, CEI is equal to 1, EX, right? So let's make this a little bit simple. So you take 2 outside, so you have 1 over 2. Just take this 2 out of the integral. So that means if you have the moment relation, plug it here, take the derivative, and evaluate this integral, you get deflection at C. But don't forget, at the end, we should put P is equal to 0, because there is no P here. We just put it to find the energy function, right? So, let's do that. This becomes half of derivative with respect to P, integral 0 to 2, m squared dx. And what's the moment? At any section, let's say x. Here, section from left, x. You have mx. So what can I write for moment? mx positive plus 2k every side. X minus 1 negative 2 plus p times x plus 2 times p plus 1 is equal to 0, right? Zeroth moment equation at x, summation of moment at this point. So you get positive mx plus 2k times every side x minus 1. So that's what it comes. Now here, the reaction, because it's not a constant, is a function of p. Then you say 2 plus p times x. Positive or negative? Negative. Plus 2 times p plus 1. This is the moment at 1. But look, don't freak out. This is just p. Right? Previously we had p 0, the integration. So you solve for m, and then you put it here. So the moment becomes take to the right, so you get 2 plus p times x minus 2 times p plus 1 minus 2k every side, x minus 1 to the square. So what you do, you take this integral, take the derivative, and finally you put, after you do all this calculation, you put p is equal to 0. That's what you do for next homework. So do that and return it to me as an next homework. Also, you can simplify that. You see, it's just one line. You see, this is the energy method. This was double integration. This is the energy method. No boundary condition. Now you can simplify. How can you simplify? Before you take that integral, you can take this derivative inside. So that becomes 2 times whatever you have to the first power times the derivative of each term with respect to p. Right? Here, integral of f of m, f of p. Right? dx. If you take derivative with respect to p, you can say integral x df p dp dx. This is basic calculus, right? You can take the derivative inside the integral. That makes your integral to be extremely easy before you expand. Because if you don't take this derivative inside the integral, you have to first expand this square term, take the entire integral, apply the bounds, and then you should take the derivative. That's what I'm saying, take it inside the integral. That should be all for today.